So, next week we'll be visited by John Aycock, who's a professor at the University of Calgary. And the University of Calgary is in Calgary, the province of Alberta, Canada. This semester he's the farthest, travels the farthest for giving himself some latitude here. Anyway, that's next week. Today I have the pleasure of introducing you to Nora Ayanian, who is Gabilan professor of the world prestigious Viterbi School of Engineering at the University of Southern California. And she's here to tell us what to do in case we have too many robots. So let's welcome our speaker.
Thank you so much for the introduction. I would like to make the case that there's no such thing as too many robots. But it's a pleasure to be here today to talk to you about my work in multi-robot coordination. So multi-robot systems is an area that has applications in a lot of different industries, for example, manufacturing, warehousing, surveillance, in the military. And so the results in multi-robot systems come from a lot of these different areas, and so it's a very fragmented field. And so I would like to argue that in order to have a real impact with multi-robot systems, we need to come up with some unified approaches that can be easily applied in different areas. So my research vision is really to come up with a theoretical basis for a coherent, unifying framework for multi-robot coordination. So let's think of a simple example. So here we have an environment where maybe we want to do some environmental monitoring, take some measurements. So what we might want to do is we might want to deploy some aerial robots in order to take air measurements, some ground robots, and some water robots as well. And so the way that we normally handle this in multi-robot systems is first we'll develop a set of controllers for these aerial robots. Then we'll develop a set of controllers for the ground robots. Then we'll develop a set of controllers for these underwater robots, and it becomes really messy. And it's hard to take code that starts with these kinds of applications and then transfer it to another application. And so what we really want to come up with is some end-to-end process that starts with a high-level specification and then delivers code for the individual robots in the team automatically without really having to do a lot of work. So let's say I want to develop an iPad app to help me do this, and I should really just be able to put in my multi-touch inputs and then be able to control this team of robots. And what we want to come up with are provably correct algorithms, so algorithms that are guaranteed to converge to the goal. They're guaranteed to work every time. And this is so that we help establish a science of multi-robot systems. So there's been a lot of progress in multi-robot systems. So for one example, they've been used a lot in manufacturing, for cars specifically. In warehousing, I'm sure many of you are familiar with Amazon Prime, which gets you your packages as soon as possible, and they do this with the help of robots in their warehouses. And also, they've been used a lot in the military. But the difference here, the difference between these applications here and applications that we're interested in, are that these are, they're very hand-trained, especially in manufacturing. These robots have very limited capabilities. The environments are very structured, so they're not very free-form. The interactions between robots and humans are very engineered. And in the military, for example, they're always teleoperated, which I think is actually a good thing. And so some of the areas that we actually want to be able to use robots are in emergency response, in transportation, or in automated delivery. And these are very unstructured environments where there's going to be a lot of interactions between the robots, a lot of interactions between robots and other things, and we're not able to tell in advance exactly what we want the robots to do. So this brings us to some of the challenges that we have in multi-robot coordination. So number one, we really want the controllers to be developed automatically. I want to put in my inputs, tell the robots what I want to do, but I don't want to have to fiddle around with the controllers and have to hand tune them for each robot. I just want them to work. On top of that, I need guaranteed performance. I want them to work every time, no matter what. So I don't want to have to send in my robots to survey a forest fire and then half of them drop out of the sky. I also want them to operate safely. So this means that they can't collide with each other, especially aerial robots. They can't collide with obstacles in the environment, and they, of course, can't collide with people. On top of that, we have the challenge of dimensionality and combinatorics. So we have n robots. There's so many ways that I can make these n robots do n different tasks. So how do we overcome these challenges and determine which robot should do which part of which task? So these are the challenges that I'll address in my talk today. So let's take another simple example. Let's say I have a team of robots, aerial robots, and I want them to navigate to this orange blob up here. So arguably the easiest way is just to take the shortest path, but that would actually run us through this area where we have unfriendly agents that might shoot down our drones. So we have two options. We can go here, or we can go here. But how do the robots actually decide which way to go? Well, this is a difficult problem because there's risks inherent over here, and there's other risks over here. And so we need to be able to come up with a way that we can actually solve this problem without having to have some expert come in and figure out, okay, I'm going to come up with some new heuristic to figure out that the robots should go this way or that way based on whatever risk that we have. But the nice thing about the unified approach, about solving kind of all of these different challenges in one so that we can basically make a very simple and succinct app that will help us do this, is that we can easily put in operator input without overhead. So if I had to actually code up the controller, then it would take a lot of time for me to change my mind, right? If I came up with some new risks, then I wouldn't be able to come up with a heuristic for them and pop them into my code really easily. This way, we have an operator that can easily change the course or set different goals for the robots. On top of that, when we have this kind of simple interface, we are ready for unpredictable scenarios. So let's say we decided that we should go this way because maybe it's safer to go over land than it is to go over water. But what happens is we actually drive this way, and now we see that there's unfriendly agents over here too. And if we didn't have an app where we could easily change our mind and easily come up with automatically synthesized controllers, then it would be really difficult for us to reroute and decide to go this way. So there's been a lot of related work in multi-agent coordination and multi-robot coordination, but they generally work in different silos. So there's 4 different areas. One is specification and interfaces. Another is task allocation, determining which robot should do which part of which task. Then there's path planning, so actually driving to the task location. And then, of course, there's control, which helps us kind of stay on that path. But I would argue that you can't operate in these 4 separate silos, and that all of them should actually be together. They should be solved together. So my work actually combines all of these 4, and we solve it in a unified way. So while we can actually divide some of my work into specification, coordination, planning, and control, I would argue that anything that I'm going to talk about today fits into almost all of these different areas. And I think that this is an important way to solve these problems, because I could, for example, I could optimize which robot should do which task, but if I don't know that there's a path that will actually take me to that task, then all of that optimization is for naught. So today I'm going to talk about control policies that we can come up with when we're keeping in mind the specification that we want. So if we want an iPad app, we need to know the limitations of that iPad so that we can come up with controllers that can be specified that way. Then I'll talk about modeling, planning, and control for multi-robot systems, which lays the foundation for my work. Then we'll talk about how we can actually decentralize those control policies and then actually use them in environments where we don't know everything. And then finally, I'll talk briefly about human-inspired control. We generally come up with robot controllers in a silo anyway, even though I'm working on all of these different areas together. Robots are not human, but there's a lot that we can actually learn from humans. And so I'll conclude the talk with that. Okay, so first I'll talk about how we can come up with control policies with specification in mind. So let's go back to our example. So we had our robots that wanted to navigate to this orange blob over here, but the shortest path was cut off by these unfriendly agents. So when we're actually deciding which way to go, we need to have some interface in order to be able to tell the robots what we want to do. And the interface for a single robot can be nice and simple. So here's an example. Here's the interface for the ghost drone. Basically, I use my phone and I just kind of tap where I want the robot to go. And this is really simple, right? Very easy. But now imagine that I have 3 robots. I'm running out of fingers, right? I can't use the same kind of interface. I need a very specialized interface so that I can deal with this multi-robot system. And so generally when we come up with robot controllers, what we do is we work from the bottom up. So we have our robots, and then we have the governing equations for those robots, and then we sit down and we write a ton of code, and in the end we need 3 people to run a team of 3 robots, which is just not sustainable. If I want to run 100 robots, I can't have 100 people running them. And so the traditional bottom-up approach means that usability is actually an afterthought. So we're not taking usability into account because we're starting from the bottom up. But usability is actually really important. So with usability, we can actually reduce manning, right? We won't have to have as many people as we have robots. We can allow quick reactivity because imagine if you have 3 people and they're trying to agree on what to do next. This actually delays it a lot more. It enables hardware changes so that now actually I don't have to work from the bottom up and determine all of my code based on the governing equations of my robots. And on top of that, you can maintain situational awareness, which means that the operator can have all of the information in front of them and deal with all of that information instead of just bits and pieces. So what we want to do is we want to develop a novel control algorithm or a control policy that lends itself well to inputs from tablets or smartphones, for example, and also enables user input for cognitive tasks. So trying to decide if I should go right or left is something that could be really hard for a robot if we haven't foreseen all of the scenarios that could occur. So we take a thoughtful top-down approach. So I want one person to be able to operate my team of robots. I want them to interface with them using an iPad app. So with that iPad app in mind, I can write all of the code that I want, and then I can control this team of robots using my simple iPad app. But there are definitely challenges that come with thinking about the interface first. So the iPad, of course, we can use multi-touch inputs. But there isn't really a good way of doing kind of complex interaction with the system. It's not something that I'm going to want to break out a keyboard and actually type stuff on, right? I really just want simple touch commands. And so what we were thinking about while developing these controllers is that we actually need to make an abstraction. So we need to kind of simplify the way that we interact with this team of robots because we only have multi-touch inputs. So one thing that we thought is, let's say that we have a map of the environment that's shown on our iPad. And let's say that we surround all of the robots with a rectangle. So I'm going to say rectangle because it's easier to say than rectangular prism. But this is not limited to 2D. We also did this in 3D. And so let's say that my robots are surrounded by a rectangle. One easy thing I could do is if I have the environment mapped on my iPad and I can see the robots, is I can just take that rectangle that surrounds those robots and I can just maneuver that rectangle through the space. And then basically the robots will have to follow that imaginary rectangle or the environmental abstraction as I maneuver it through the space. So I have my robots here, and now I'm just going to move this rectangle, and then as I move the rectangle, the robots move with it. So this is, it's kind of an obvious choice. It's good. But unfortunately, it means that all robots have to be in the same cell, right? They have to all share this rectangle at all times. And this can actually cause the robots to have to communicate a lot. It can cause drainage of power because they have to coordinate so that they don't collide with each other. So another thing that we thought of is actually to draw multiple overlapping cells in the environment. So now instead of taking this one rectangle and basically drawing it across the screen, now I can just draw multiple rectangles. So I'll first draw one rectangle around my robots, and then I'll draw another one that overlaps and another one that overlaps. And then I can take the union of all of these as the space that the robots are allowed to be in, and I can let them flow through that set of rectangles. This actually is nice because it allows the robots to spread out. So we get to do a little bit less as far as collision management goes. However, this works great in 2D, and if we were simply doing this in 2D, then it would be fabulous. But it's too difficult to draw cells in 3D on an iPad, right? Imagine, it's simple to draw a rectangle. I could just, draw one point and draw the other one, and then draw one point and draw the other one. But how do I do this in 3D? So if I want to actually control aerial robots with this app, then this is not going to work. So finally, we came up with the idea of taking this, of kind of combining these two. So we take the single cell where the robots start in, and we manipulate that as we move along the screen, just like we did here. Except now, we take the union of all of these rectangles that are generated. So we take screenshots at every half a second or every 10th of a second, and we save those rectangles, and then we take the union of them, and we allow the robots to kind of flow through this. So this allows spread, which is great. So we have less collision management, and it's much easier than drawing individual prisms in 3D, right? So this translates really well to 3D. We end up with a little bit more complex space that the robots have to flow through, but at least it translates well to three-dimensional systems. And so basically on this app, what we can do is we can translate the rectangle by dragging, so just by dragging a single finger on the screen. So this is actually, so here we have our 3D view, and then we can have orthogonal views here. And I can scale the rectangle by pinching, just like you would anything else, just like you would to increase the zoom on your browser, on your cell phone. And then at the initial state, the robots are surrounded by a rectangle. I'm sorry, it's a little bit hard to see, but this is the rectangle, and we have 3 robots in here. And then I can essentially lift up that rectangle so that the robots are now flying, and then I can manipulate it however I want. Great, but how do we actually come up with controllers that'll do this? Well, we need the robots to actually flow through all these rectangles as we kind of drag them on the screen. And so one way that we can do that is to allow them to kind of flow from one rectangle to the next one in the series by kind of pushing them towards the center. And if we make sure that any second rectangle overlaps the center of the first one, then as long as the robots all kind of tend towards the center, then the robots will be able to transition to the next one. So if there's a robot over here, then it's going to get pushed inward, and then now that it's here, it transitions to this one, and they can do the same thing over and over again sequentially. So we come up with a controller that kind of pushes inward from the boundaries of the rectangle so that the robot can transition to the next rectangle. But now, of course, we have to deal with collisions. So what we do is we want the robots to maintain a safe distance between them. So at some really close distance, then we have some infinite force, some really high number that pushes the robots away. At another limit, this kind of decreases to 0. So we have a really high force, and it kind of decreases to 0 as we reach the interaction limit. And then beyond the interaction limit, we allow the robots to kind of talk so that they know if somebody's coming into their interaction zone. But otherwise, if they're far away, we don't even care. We can have as many robots as possible. If they're spread out, they don't even have to talk to each other. So basically, we sum these two together. And both of them are just inverse exponentials. So we sum these two inverse exponentials together, and now we have a controller that'll actually drive the system to the goal configuration. This is actually susceptible to local minima. So when you sum these kinds of controllers together, you could have local minima where the robots actually get stuck. We can do some neat tricks with randomization to allow the robots to kind of get unstuck and continue going to the goal. So we can actually prove that we get to the end configuration. So this is what it looks like. So this is me actually controlling the iPad. And this is my friend over here. He has a remote control, but it's just emergency stop purposes. He's not actually controlling anything. So we have 3 quadrotors, and this is our environment. We have a table in the middle. I just lifted up the rectangle so that the robots would take off. And everything is done in real time. The robots have no idea what I'm going to tell them to do. They're just doing it as I go. And you can see the robots are a little bit shaky. That's because we didn't actually tune the controller. So I told you in the beginning that my work develops automatically synthesized controllers. And so while we can actually tune them to make them work better, we actually don't have to. Granted, if you were coming up with a product, you probably wouldn't want them to work this way. But in the lab, it works fine. And if you're coming up with a product, you have a little bit more time to come up with some better tuning parameters. And you can see that the robots safely get to the other side of the table. And here we can show this in an overhead view. So this is sped up 8 times. So they're really not that jumpy while they're moving, but they are moving pretty slowly. So again, all done in real time. The robots have no idea what I'm going to tell them to do. All of the information gets passed from the iPad app to the robots. So this is really cool. But we also need to think about controllers that can really work for a lot of different things. So this was a very specialized controller for the iPad app. And we need to think also about how can we actually come up with controllers that work for a wide variety of things that actually don't need hand tuning, just like the iPad app controller. So it's important when thinking about these controllers to think about what the robots actually can do. And we model actually robots as kinematic, so single or double integrators, which is not accurate, especially for a quad rotor such as this one. But it's an approximation, and we're going to deal with this in the feedback control. So we have these robot models, single or double integrator, and these robots operate in a configuration space. So the configuration space is the space of all possible positions that a physical system can attain. And we tessellate these into convex regions. So if we have different kinds of robots that are operating in the same environment, their configuration space will look different. Some of them are bigger, some of them are smaller, some of them fly, some of them might be on the ground. And so the environment might actually look different for different robots. And what we're going to do is we tessellate this into convex regions because we want to be able to sequentially compose controllers for these robots. And what do I mean by that is I want to have one controller in here, and then another controller in here, and then another one in here, so that I can easily piece together these kind of building blocks of controllers, and that they can translate well from one application to another. And the truth is, we do this all the time. So when we're giving directions to someone, we might say, keep going on Petaluma Hill Road, and then make a right on Kotati Avenue, right? We're not going to say, okay, now drive 0.5 meters, and then stop, and then turn 90 degrees to the right. This is not the way that we actually interact with others. And so we actually use sequential composition. So you drive straight, and then you turn right, and then you go straight, and then you turn left. So we're essentially sequentially composing controllers all the time. So why not have the robots actually do this as well? So what we need to do first is I'm going to define something called a polytope. So a polytope is the convex hull of a finite set of points in d dimensions. So this is just kind of a generalization of a convex polygon, right? So just going up into higher dimensions. So 3D, 4D, 5D, 16D, however many Ds you want. So what we're going to end up with is a space of convex polytopes where we can easily come up with controllers that translate from one polytope to another, and they can be easily developed. So one thing that we also need to think about is inter-robot constraints. So we want the robots maybe to stay within communication, and we definitely want them to not collide with each other. So a normal communication model might be if the robot is this black dot over here, then another robot that's within this red disk should be able to communicate with it. This is called the disk model of communication, and it's absolutely wrong. Communication doesn't look like this, as I'm sure you know from trying to get Wi-Fi. It's not a perfect disk around your router, right? So I would argue that these two models are equally good, right? Or equally bad, I should say. And so what we do is we opt for this. So we use a square, and the reason for that is that it really simplifies our math. So why go with something that is bad and is complex when we can come up with something that's just as bad, but very simple? So we take this option, and so if there's a robot at the center here, and we want another robot to maintain communication with it, then we want that robot to be within this red square. So similarly, if we have a robot in the center here, and we wanted to avoid collisions with another robot, then that other robot has to be somewhere outside this blue square. And then we can combine the two. And when we combine them, we have to tessellate this again into convex regions, so that in the end, we end up with convex polytopes. So you're not actually fixed to a square. You can use any kind of arbitrary tessellation that you want, as long as it lends itself to convex regions. But we're going to go with a square since it's simple. So we have our workspace. So we have so here we have 6 robots, and each of them might have a different workspace. Like I said, some of them might be aerial, some of them might be ground. And we have our relative space constraints where We want the robots to maintain communication and to avoid collisions. And so what we do is we intersect them. So when we intersect them, we end up with a high-dimensional space. I'm drawing it in 2D for simplicity, that we call the task configuration space. And in the task configuration space, the robots can't collide, they can't lose communication, they can't basically break any of the rules that we set up here. And so this task configuration space contains one point that corresponds to the goal for our team of robots. So that one point is in however many dimensions. So we have 6 robots. Let's say they're ground robots, so this is a 12-dimensional space. And in this 12-dimensional space, one point describes the goal location for all of the robots. And so we can actually build a connectivity graph while simultaneously searching for a path to the goal. We don't actually have to build the whole space because the 12D space could be really hard to build. But we can use some novel A-star search modifications so that we can come up with a path to the goal at the same time that we build the space that we need. And so then what we do is we construct feedback controllers that will actually drive the team of robots to that goal. So we can find this path through the task configuration space, and then we build individual controllers that will push the team of robots to the goal location. So why do we actually care about feedback control? So number one, our robots are susceptible to a lot of noise. And so here's an example of a robot that's moving. It slips on the ground. And if I don't have feedback control, then it might actually end up somewhere that I don't want it to because it's slightly turned. And as it slightly turns, it might just keep going in the direction it thinks it's going in and totally mess everything up. Another problem is that we have network latency. So when robots communicate with each other or with a server, the commands might come in a little bit late. And so you need to be able to kind of accommodate for any changes that might have occurred. And then finally, we're approximating our robot models. Remember that I said that the quadrotor is a highly dynamical system, and it's kind of silly that we're approximating it as a double integrator. But the feedback control is going to help us accommodate for this. And we have another trick that'll help us do that as well. So in feedback control, there's been a lot of work. So there's been a bunch of work on sequential composition. So actually coming up with controllers that we can piece together to get a kind of global behavior. And there's been some work in potential functions, namely in navigation functions, which is what we're actually going to use a little bit of. The problem with navigation functions is that they're very complex. But one thing that's an advantage of some of these sequential composition approaches are that they're analytical. And analytical is really nice because we have some nice equations that we can manipulate to do whatever we want. But we also want them to be high dimensional. Remember that we were talking about a 16-dimensional space. So we want these controllers to be able to work in high dimensional spaces. So we come up with a kind of combination of some of these controllers so that we can develop these 16D or however many dimensions we want and make sure that they're also analytical. So if any of you are familiar with navigation functions, maybe not, essentially what a navigation function is it basically maps the space to what's called a sphere world, which is kind of arbitrary, but basically you can imagine that this round area is the space that we're allowed to be in. These 3 kind of pop-up things are obstacles, and then this point at the very bottom is our goal. So if I take a marble and I release it anywhere in the space, it'll end up at the goal. With navigation functions, we can guarantee convergence. So you're guaranteed to get to the goal without any hand tuning if there's no obstacles. If there's obstacles, then what happens is you might end up with some local minima and you have to do some hand tuning. So these obstacles might lead to local minima, so you have to tune, but also these are closed systems. So the state can actually not exit the boundary. So once I drop that marble, there's no way it's coming out, right? It's staying in there. And so this could actually be a bad thing because we have these individual polytopes and we actually want the state to exit them from a specific place. So what we do is we take our polytope, so let's say this is where we start and this is our goal configuration, and we actually extend that polytope into the next one. So it maintains its convexity, and now we can come up with a navigation function and it'll travel along the negative gradient and actually get to the goal. And we can do this over and over again until we get to our goal configuration. And these are actually very fast to compute because we don't have to do any hand tuning. There's no obstacles inside here, which is a huge bonus. So it's great. Navigation functions are also analytical, which then means that the output of this navigation function can be easily modified. And why would we want to do that? Well, because, like I said, we're using these really poor models for our robots. So we use a single integrator or a double integrator. And so what we do is normally for a single integrator, you just follow the negative gradient of that navigation function. It will take you right to the goal. For a double integrator, you add like a damping term. But we have something that's a lot more complex, right? The quad order is much more complex than just a simple double integrator. And so we use this embedding. And what this embedding allows us to do is it allows us to modify the behavior of the system so that it kind of acts like a double or a single integrator. And so this requires a little bit of tuning, but once you tune it for one system, you're good to go. You don't have to do it again. So these controllers are provably correct by construction. So the robots will never collide with each other because we removed all the points that dealt with collision. They never lose communication if we want them to maintain it, and we can guarantee convergence because we have that nice benefit of the navigation functions. It's also complete. We don't actually lose information when we're building the map, and so if a solution exists, we'll actually find it. And of course, they're automatically synthesized. They don't require any hand tuning, and so we just set it and forget it, and it's good to go. Unfortunately, the complexity is pretty high, right? 16-dimensional space, not so great. And so the complexity is exponential in the number of robots. So one thing that we can do is we can actually come up with a way to use these controllers in a decentralized way. And that's what I'm going to do now. So robots that are really far away from each other shouldn't really have to coordinate. If I'm in San Francisco and someone else is in LA, then why should we even have to talk about what we're doing? But unfortunately, this is how a lot of multi-robot controllers work. So let's say, for example, we have 2 passengers who want to get an Uber. And so we have an Uber that's traveling south here and an Uber that's traveling north here. So if we do something really naive, we can just assign the Ubers to the closest passengers. And this ends up being really bad because there's a bunch of one-way streets here. And so it's not so simple for each of these drivers to get to their passenger. And so if we actually allow them to switch, this, using a Euclidean method is actually longer, but as far as the path that the Ubers have to travel is much shorter. And so we allow the robots to swap tasks when it's beneficial. So as long as it reduces the cost, why not actually allow robots to swap tasks? So why have them kind of work around each other when they can work with each other? On top of that, we only want them to coordinate when in close proximity. So coordination actually has a cost. And so if they're in totally different cities, there's really no need for 2 robots to cooperate, right? And so if there's other passengers that are out here, then these 2, they don't have to care about them. So why does this actually work? So let's take this simple example. So we have 2 goals and 2 robots. Now if we assign the robots such that the blue one should go here and the red one should go here, or if we assign them this way, we have the same heuristic cost. So the red robot has to travel 3 and the blue robot 1. So the total heuristic cost is 4, and here's the same. So the red robot travels 2 and the blue robot travels 2. So while the heuristic cost is the same, the actual cost is not. Because we used this simple heuristic, which just told us that the red robot is 3 hops away from the red goal. But as a matter of fact, it has to move around the blue robot in order to get there. And so the actual cost here is 6, while the actual cost here is 4. So there is this, the joint space actually captures the coordination costs for the robots. And so we want to exploit what we get out of the joint space so that we can come up with better task assignments if they're poorly assigned in the first place. Now consider the example where we don't actually have that extra space above for the red robot to move around the blue robot. So while the heuristic costs here are the same, again, the actual cost here is infinite. So there's actually no way that this red robot is ever going to get to this goal. And so there is this natural coupling between task assignment, path planning, and control that we really would like to exploit. So how does it actually work? So we have a robot here and a robot here, and as they kind of move along, they come within communication, they plan in their joint space, and they decide to actually swap tasks. So now the blue robot's going to go down here, and the red robot's going to go back up there. So we can prove here that the result is globally asymptotically stable, but only if the robots switch when the cost gets lowered. So if they switch when the cost is the same, then you can end up with switching back and forth any number of times. So I'll show you a quick demonstration. So we have robots that are in a parallel configuration, and now we want them to actually surround some target from above. So this is our initial task assignment, and then if we allow them to reassign, then we have this nice, much more succinct kind of assignment. So here's what that actually looks like. Again, we didn't actually tune the controllers. We allowed the robots to use the entire space. So this is not the most energy efficient way of doing it, but the robots kind of split up and they head to their task location. So while it takes a little bit long, they don't actually move that much. So here they're about to get into this formation. And voila. So we can also do the same thing for the next assignment. So in the next assignment, we want them to surround the target from below, and we can simplify the assignment by swapping tasks. But this assumes that we know everything about the environment. So what actually happens if we don't know everything about the environment? Well, we can use these controllers and allow the robots to share information as they collect it. So let's take this example. So we have 4 robots. And they're supposed to navigate to their goals, but they don't know about this area which they can't actually pass. So what we'd like to do is we'd like to have the robots kind of plan individually to their goals, but when they collect some information, they can keep that information and then share it with others as they encounter them, as they maneuver through the environment. So the way that this works is, so we have 2 robots, red and blue, and they have their coordinating goals, and there's this area where the robots are not able to pass, but they actually don't have this information yet. So the robots communicate. They decide it's actually better to swap goals because it shortens each of their paths. So they plan in their joint space and they swap. But as they navigate to their new goals, they discover a hazard. And so they kind of keep this information, and then when they come back, they replan, they come back, they can share that information with the other one. And now they can actually each navigate to their goal. So in this case, the robots actually did make a poor decision, right? So because they didn't know about this obstacle, they thought that they were choosing a shorter path, but they actually chose a longer one. So the cost actually might increase, but this only happens until we know what the environment is, or until we know the parts of the environment that are relevant. So here's what this looks like as an experiment. So we have the robots. They don't know about this obstacle here. They each plan individually, so we're pretending this is a much larger space than it actually is, so they're far away. Now they come into communication and they swap goals. And so now this guy discovers the hazard, and next this one will discover the hazard, so it realizes I can't actually get to my goal up here, so I have to go around this way. And the robots essentially continue switching until they actually end up right back where they started, because they don't actually know about the goals of the other robots until they encounter them. And so this, the idea is that if you have a really large space, and let's say maybe the robots are delivering packages or something, they pick up a package and they have to deliver that to a specific location, but it's better if somebody else delivers it. So here the robots are acting kind of funny. And part of this is because we have this overhead tracking system. And at the time that I ran this experiment, the overhead tracking system was missing 2 cameras. And so we can overcome this unfortunate event using feedback control because we didn't really have perfect information as to the robot's location. All right. So, like I said, this is all great, and robots acting like robots, but humans are actually really good at coordination. And so why can't we learn something from humans and inform our multi-robot controllers? So we've taken a lot of inspiration in robotics from different kinds of animals like ants and fish and lions and many, many birds, many different kinds of animals. But there really hasn't been a lot in robotics for inspiration from human coordination. And so one question that I might ask is, can teams of robots act like humans? Because we've asked and answered, can teams of robots act like fish? Can they act like ants? But we haven't answered, can teams of robots act like humans? So the inspiration for this project came from a collaboration with my postdoc group at MIT and this dance company called Polytopes. Essentially, they gave 200 people umbrellas with color-changing LEDs, so you could change the color of your umbrella. And these weren't scientists, they were just, the public. And they put them on a football field, and they had an overhead camera, and the people could see what the overhead camera was seeing. So they had this global feedback of what the image actually was from above, and they asked them to spell words like tech and pop and MIT, whatever. So humans were actually really good at this task. So can we actually get robots to do these kinds of things? So here's my team of robots. Of course, they look nothing like humans, right? I'm not going to give them color-changing umbrellas, but robots have a lot of constraints on communication, on motion, on sensing and processing. So robots not equal to humans. And so humans actually have, it's kind of hard to see, but one of the participants here is actually pointing and talking to someone. This is something that would be impossible for the robots to do. Unless I knew, exactly who I was going to be sending that message to, and I could, send them a message over like IP or something. There's no way that I could have robots do these kinds of things. And so maybe the better question to ask might be, can humans coordinate under robot-like conditions? So robots have all these constraints that humans don't really have. And so if we constrain humans to act in the way that robots do, can they actually do interesting things? So we did just that. So what we did was we developed an online game. And in this online game, we asked players to do complex coordination tasks like making shapes. So if you're the player of this game, this is your local view. So here's you. You're cyan colored. And you can see kind of what a robot would see based on having a laser rangefinder. So the laser rangefinder, you're not going to be able to see the color of other people that are around you. And of course, there's a boundary as to how far you can really have reliable information. And so you have this local view, and you have a global view. So this global view actually doesn't show all of the space that you're allowed to travel. There's actually an area around it where the camera can't see, so you can kind of get lost. And so you can change your color, and basically you can tell us, this is just for analyzing purposes, that you know where you are in the world, so you're localized, or that you're done. You think that you don't really have to move again. So we asked people to do tasks like form an empty rectangle. So when I play this video, note that there's this guy, number 2. I'm not sure if you can read the number, but he does some interesting things to kind of get these other people to kind of move out. So everybody kind of played this in the same room. Although we didn't allow them to talk, we gave them earplugs. They couldn't see each other's screens. So we had like 20, 25 people playing this game. And here they had both this global view and also the local view. So here we go. So here at the bottom you can see that, where is it? There's basically, robots kind of move in interesting patterns so that they can figure out where they are in the world. They'll also kind of swap colors. So here you can see number 2 looking crazy, but it's at 4 times speed. And what number 2 is trying to do is they're trying to get these other people to move out, like make space. This rectangle is too small. We're not all going to fit here. And so it came up with these methods for signaling when we actually took away language. We didn't allow them to talk to each other. We didn't give them any kind of robot-like communication capabilities, but they came up with communication anyway. And so they formed a halfway decent rectangle. But that one last guy was kind of off the screen, so he didn't show up in the global view. So, okay, so now what happens when we don't have any local feedback? So we take away that local feedback where you can see yourself and the other agents that are around you, and we just give them a global view. On top of that, we made this all one color. So imagine how easy it is to localize yourself when you're red and everybody around you is blue. But now imagine that everybody's red. So this actually becomes a much more difficult problem to localize. And in the end, they actually build a nice circle. So here we go. This guy's actually going down to the bottom. So this is actually off the screen. So the black area is the area that you can see in the global view. And so one way that you can localize is to exit that and then come back in. And so when you come back in, you can see when you've kind of come to the edge of the screen in the global view, and then you know that which one you actually are. And so with the global view, this is actually only 2x. This is so the last one that I showed you was the first time that those players had actually played any of these games, and this is the 4th time. So they're getting pretty good at it, but with the global view, they do consistently better. So if you take away the global view, and I'll show you that video next, it takes forever. And you can imagine why. Okay, now we have only the local view. So basically, you can only see like a couple a couple agents away from you, right? You can't see the entire thing. And so what we asked them to do is we asked them to build a square. And you can see that, this is kind of halfway through. What you can see is that because they only have a local view. You can really only see, if I'm this guy, I can only see this area around me. I don't even know that this other group exists. So they have a single color. This is actually sped up 8x. So you can see that these rectangles start forming in many different places. And it actually takes a really long time for them to realize that, wait a minute, we really don't have a lot of people. So as they move around, they kind of count, and they know that there was 25 people playing the game. And so what they do is they realize, oh, this is not good, and they end up dissolving, but they still don't really know where to go. And so now they get here. Eventually, everybody figures it out. They all end up at the same place. We did ask them to form a rectangle, so not a square. So here, the problem is that they're almost there, right? But nobody's sure. Nobody's sure that they've actually made this rectangle. And so what they do is one person will go out, kind of run around and say, okay, I'm good, I'm going to go back to my spot. And then another person will do the same thing, and another person. And so they kind of keep doing this ad nauseum. But it does end eventually, and they do come up with a pretty good rectangle. I'm going to leave it at that. So the questions that we'd like to answer with this project are, what transferable skills can we learn? So one, we can learn ways that people localize. So this guy is changing color and moving in one direction, so you can see that on the global view and understand that, who he is. Another way to localize is also by being a different color than everybody else. So this one guy in many of the games kept the same exact color, and then at the last minute changed, because this way he could keep track that he was the one that was that person. And also signaling. So here, this is another way of signaling. So number 2 is kind of bumping into other people to try to get them to do something. And then you'll see here, there's this one guy who's kind of out in the middle of nowhere, and this other one is trying to go and convince him to come. So the other thing is, are traits inherent? So do people actually play the same way through multiple games? And we learned that sometimes they do, sometimes they don't. How do they actually reach consensus? How do they decide that the rectangle or the circle is properly formed? And how much diversity is necessary? So there were multiple rectangles that were forming in the local view only version. And so what happened is, one group was more stubborn than the other one, right? So diversity is kind of inherent, and I think that the way that humans actually coordinate is kind of geared towards diversity, right? Everybody has different things that they're good at, and so this actually makes things work. And so the idea is that we can take some of this diversity and actually put it into a robot controller and come up with different controllers that do kind of the same thing. So I've talked about a lot of my work that spans a lot of these areas, but I have other projects and I'm running out of time, so I can't tell you about some of my future work, except that one of the projects that we're working on is to actually deliver power to robots. And so instead of having robots go back and charge, we actually bring the charge to them, or other resources as well. We also have some work where we are using kind of robots to do virtual reality. So we can take any environment and allow, for example, soldiers to train in a desert but pretend that they're in an urban environment by using quadrotors with cameras to track them and kind of put those images into the virtual environment. Another thing that we're trying to do is this is not our project, this is National Geographic, but the idea is to use quadrotors to do kind of 3D reconstruction of animals in the wild. So you need to have some very good coverage on them and come up with novel ways of using your sensor. So this is just an example of a robot that was actually in that kind of environment. And we're also coming up with novel ways to do experiments when you don't have all the resources that you need. For example, you have a small space, you want to run lots of robots. Those robots are usually not that capable. All right. So I've talked to you about my research vision on coming up with unified ways of solving these multi-robot coordination problems. And I really feel like this is necessary in order to develop a science of multi-robot systems so that we can easily take controllers from one aspect and move them to another. So of course I'd like to thank my students who've been working on this, undergrads, grad students alike, and our funding agencies, Army Research Lab, Office of Naval Research, and the National Science Foundation. So you guys have been a really great audience, and I'll take any questions if we have time. Thanks.
We have time for one or two questions.
If a student who is sitting here now wants to be in your shoes in a few years, what math do they need to take?
Oh, differential equations. Yeah, I think that, that you have to go at least that far. Differential equations. I actually took some topology classes, which sounds like not a lot of fun, but I actually really enjoyed it. But topology could also be really helpful. Group theory, those kinds of things.
You kind of mentioned at the end, like using, I think the term you used was like mixed reality or something to model robots. Like, how effective can you model these robots so that you don't have to have 20 quad rotors to test these things?
Yeah, so we're actually working on that. So the nice thing is that with the mixed reality, we can run robots in the real world, but give them kind of virtual capabilities, like a virtual camera. So in this video, essentially we have this tiny little quad rotor, and we're equipping it with a virtual camera. So the quad rotor can actually carry a camera. So this is the virtual world, we're giving it a camera. But the nice thing is that we actually have the robot that's moving in a real way. Whereas simulated robots are perfect, right? We have a good enough model for them, and they're not susceptible to wind or anything because they're all simulated. So what we're trying to do now is we're trying to learn, the models, including models of noise, that we can kind of impose on virtual robots. So we've run in this space with actually 6 of these quad rotors plus 6 virtual ones, and I mean, the virtual ones are perfect, right? So they're not actually, it's not as meaningful. So we're trying to come up with models so that we can actually make it more meaningful.
Have you considered presenting the human part to the political science department?
I'm not sure if I should answer that question.
Or sociology.
So actually I have a collaborator in communications, not like wireless communications, but people communications at USC, who we're working a little bit with on that. She actually studies small group theory, so how do small groups actually work together? So it's a very synergistic relationship there.
No more questions? Okay, well, thank you.